Welcome to the Mechanics of Solids lecture series. In this series of videos, we're solving for internal shear and moment functions in beams. The lesson objectives, what I want you to be able to do at the end of the lesson, is to evaluate support reactions in statically determinate beams, go on to analyze the beam to determine functions for internal shear force and internal bending moment along the length of the beam, and finally to take those shear and moment functions and plot a shear force diagram and bending moment diagram. The first example we'll look at is a problem from Mechanics of Materials by Timothy Philpott, Wiley, 3rd edition. Here's an illustration of the beam we're asked to analyze. Notice that we aren't given values. This is a symbolic representation of a class of problems where we have a point load, a concentrated force occurring somewhere in the middle of the beam. So we're asked to find the reactions, the internal shear and moment, as a function of the unknown load and the distances A and B, which represent the relative lengths of the beam between the support. Some students don't like to solve or find difficulty solving beams with symbolic loads, but recognize that it represents a class of problems rather than a single problem. And if we know the solution to this, we can apply it to many different cases. So we'll proceed to analyze this by starting with the reactions. And I'm going to take this illustration as my free body diagram. Replace the pin at A with an unknown reaction A sub y and A sub x in the x direction using slashes for reactions. I'll replace the roller at C with an unknown reaction C sub y. And I can trivially recognize that because there's no load in the x direction, my A sub x must be equal to 0. I don't mind if you skip this step in the future. To determine C sub y, I will sum moments about A. Sum of the moments about A equal to 0, positive in the counterclockwise direction. I'll start with a contribution due to C sub y. I have C sub y times the length, A plus B, that's acting in the positive direction, minus the contribution due to the force P, minus P times A equals 0. I find that C sub y equals PA divided by A plus B. To find A sub y, I'm going to sum forces in the y direction, assuming positive in the upward direction. I have A sub y plus C sub y, which we just found to be PA over A plus B, minus P equal to 0. So A sub y equals P minus PA over A plus B. To simplify, I'll multiply by 1, A plus B over A plus B. Therefore, this simplifies to PB over A plus B. Okay, we'll start with a clean sheet for the next part of the problem, replacing the unknown reactions with their known values in terms of P, A, and B, and then proceed to analyze for the shear and moment functions. Now we need to recognize that anywhere we have a change in the load, cross a concentrated force, or cross a concentrated moment, we're going to have a change in the internal shear and moment functions. So we need to divide the beam into regions and analyze each region separately. For this case, I'm going to call everything to the left of my concentrated force region 1, which is represented generally by the distance x less than A. I'm going to call everything to the right of the concentrated force region 2, which is represented generally by coordinate x greater than A. And we analyze each region independently by making a cut somewhere in the middle. So I'll start with region 1, make a cut anywhere along anywhere to the left of the concentrated force, and draw a free body diagram of the beam to the left of the cut. Okay, this is for region 1. The distance, or the length, is equal to x. Add the support reaction, and any reactions or loads that fall to the left of the cut would be included in this free body diagram. In this case, it's only the support reaction. And then at the location of the cut, I'm going to add the unknown shear, which I'll call V, drawn in the positive direction, which is assumed downward for internal shear. And then I'll draw my I'll draw the unknown moment, an arrow for the unknown moment, which I'll label M, also assumed to be positive, which is curving upward for internal moment. To find internal shear, we'll take sum of the forces in Y equal to 0. We have PB over A plus B minus V, and I'm going to express this generally as V of x to recognize that it's a function of x. Set that equal to 0, and we find V of x equals PB over A plus B. To solve for the moment, I want to sum moments, and this is very important. I'm going to sum moments at the location of the cut and not at the end of the beam. That reason I do that is so that the unknown shear drops out of the equation, and that tends to simplify things. So we take sum of the moments at x equal to 0, starting with the unknown moment itself, m of x. And in this case, the only other thing that creates a moment at x is the reaction, which is in the opposite direction, minus PB over A plus B times the distance, which is x. Set that equal to 0, and I get m of x equals PB over A plus B times x. And I'm going to move on to region 2 and do the exact same thing to find shear and moment functions for region 2. Make a cut somewhere to the right of the concentrated force. Draw a free body diagram of the entire beam to the left of that cut. Add in all the support reactions and loads that are to the left of the cut. So we have the support reaction at A. We have the concentrated force P, and this is where I'm going to label my distances. Recognize that this distance is A. I still want the total distance to be x, so the distance to the right of P would be equal to x minus A. And again, the total distance is equal to x. I will add in internal shear, drawn in the positive direction, internal moment, drawn in the positive direction. Take sum of the forces in Y equal to 0. We have PB over A plus B minus P minus V of x equal to 0. So we get V of x equals PB over A plus B minus P, and we can show that this simplifies to negative PA over A plus B. To find the moment, take sum of the moments at x equal to 0. We have m of x. As before, we have minus PBx over A plus B. And then finally we have this additional term due to the load P, which is acting in the same direction as m, so it's going to be positive, plus P and times the distance x minus A. Set that equal to 0, and I get m of x equals PBx over A plus B minus P times x plus a. The textbook that you have will often simplify this expression, and it depends on what you're going to do with it. For using this to evaluate shear and bending moment diagrams, I don't mind if you leave it in an unsimplified form, and in fact it may be easier to work with if we leave it in this form. So we'll go on to complete this problem in the next video.